Swayam Prabha. Digital India. Educated India.
I am Shrikant Raghavendran from Sastra University, belongs to Department of Mathematics. My area of experts in number theory. In number theory particularly Diophantine equations. I did my doctorate in Madras University and presently I am taking for engineering classes as well as arts and sciences for various mathematics discipline areas. Now I am going to start with mathematics for cyber security. First I will introduce where the mathematics for cyber security starts. So it starts from the word mathematics, from the numbers, pattern, sequence. Once you know the pattern and sequence, we can easily develop what is mathematics. So mathematics plays in many areas in engineering field as well as science fields. Nowadays mathematics plays main role in cyber security. So that is why the topic introduced for mathematics for cyber security in all engineering field as well as computational fields like computer application and MSc data science and so on. Now mathematics for cyber security comes under the 4 subdivision. One is called it as fundamentals of set theory and combinatorics, and second one is elementary number theory, third one is abstract algebra, fourth one is fundamentals of cryptography. Now set theory is a main important things for analyzing the number of domain and codomain ideas. It will be helpful to analyze counting principles and probabilities. So fundamentals of set theory and combinatorics gain the knowledge on the fundamentals of counting principle and probability. And elementary number theory is a comprehend the basic concept of number theory and solve the congruence equations. Fundamentals of abstract algebra is based on the understanding the nuances of algebraic structures and their applications, and fundamentals of cryptography acquire a working knowledge of various kind of cybers. Now these are all the references we have to read, and I referred these books. Starts from Discrete Mathematics and its application, written by Rosen KH, and publication is McGraw-Hill publication, 7th edition I referred, and then Number Theory for Computing by Song Y Yan, Springer Verloc, New York 2010, and then Contemporary Abstract Algebra by J. A. Gallian, published by Cengage Learning, and then the fourth references Introduction to Cryptography by R. A. Molin, the publisher is Chapman and Hall, and fifth references is Elliptic Curves, the topic is Number Theory and Cryptography by Lawrence C. Washington, and then sixth reference is Abstract Algebra, that is Theory and Applications by Orthogonal, written by Thomas W. Judson, and lastly I referred a sham series Outline of Abstract Algebra, written by Lloyd J. Singh, Frank Ayers, published by McGraw-Hill Education. So these are all the references I referred for understanding of mathematics for cyber security. Now we will go to the detailed lesson plan of Unit 1. The total mathematics for cyber security consists of 4 units. Out of 4 units, Unit 1 states that fundamentals of set theory and combinatorics comes under the title. These are all the following subdivisions. One is basics of counting principle, product rule, sum rule, subtraction rule, division rule, and we are going to discuss a few examples. And a second subdivision consists of pigeonhole principle, generalized pigeonhole principles, problems and examples. And third one, the basic permutation and combination, generalized permutation and combination, permutation with repetition and combination with repetition. Based on this, we have to discuss the problems. After that, the fifth subdivision, we are going to discuss the permutation and indistinguishable objects, and then distinguishable object and distinguishable boxes, then indistinguishable objects and distinguishable boxes, then distinguishable objects and indistinguishable boxes, then distinguishable objects and indistinguishable boxes. So, these are all the topics followed with permutation and combination. Based on this, we have to discuss the problem. After that, we should know some fundamentals of probability as well as some basic introduction of random variables, both discrete and continuous. After that, we have to learn conversion of numbers in decimal to binary and hexadecimal. Based on that, some induction is also most important. Therefore, we are going to discuss a problem on mathematical induction and strong induction, and we will continue further mathematical induction and strong induction, and further we have to discuss more problems on these areas. Now, let us start with the basic counting principle. Now, the first topic is the product rule. It means you take two tasks, one is called as N1, another one is called as N2. So, N1 ways to be first task we have to discuss, and then these ways of doing the first task as N1, and there are N2 ways to do the second task. Then the product is N1 N2 ways to the procedure of counting the principles. So, this is called as first principle of the product rule. So, we have some examples related to product rule. A new company with just 2 employees, Sanjay and Patel are the 2 members, rents a floor of a building with 12 offices. How many ways are there to assign different offices to these 2 employees? This is a question. Now, what you can understand that here 2 employees, one is Sanjay and another one is Patel, therefore, let it be N1 and N2. Now, these 2 employees corresponding work can be done in 12 ways. First, you have to choose one person is Sanjay. Sanjay can be done in 12 ways. Then assigning of the office to the Patel different from office assigned to the Sanjay will be done in 11 ways, because he already have done one ways. Followed with that, Patel is 12 ways, so that we can apply the product rule that N1 into N2, that is 12 into 11 is 13 ways, 132 ways to assign the office to the 2 employees. That is, by the product rule, there are 12 into 11 equal to 132 ways to assign office to these 2 employees. So, that way we can do for using the counting principle of the product rule. The same way we can do for second problem, that is, the chairs of an auditorium are to be labelled with an uppercase English letter followed by a positive integer not exceeding 100, what is the largest number of chairs that can be labeled differently, right? So, here we are choosing that the English letter as 26 letters. Now, we have the letter followed with the positive integer as not exceeding 100 is another number. Therefore, N1 is a English letter. It consists of 26 uppercase, and N2 is the one of the 100 possible integers, right, one of the 100 possible integers. Therefore, we apply the product rule. There are 26 into 100 is 2600 different ways that a chair can be labeled. Therefore, the largest number of chairs that can be labeled differently is 2600. So, this way we can apply for product rule. So, this is a topic comes under the counting principle. So, similarly we can do for another problem. There are 32 microcomputers in a computer center. Each microcomputer has 24 ports. How many different ports to a microcomputer in the center are there? Now, here we have to choose the two numbers. One is called it as N1, another one is called it as N2. So, here N1 is a one way, N2 is another, is a port. Therefore, the procedure of choosing the port consists of two tasks. One is picking a microcomputer, another one is picking a port on the microcomputer, because these are 32 ways to choose the microcomputer and 24 ways to choose the port, no matter which microcomputer has been selected. Therefore, the product rule shows that 32 into 24 is 768 ports, right. So, this way we can do for the product rule. Another example, how many different bit strings of length 7 are there? The solution is, so each of the 7 bits can be chosen in two ways. Either it can be 1 or 0. Therefore, the product rule is here totally two numbers. Therefore, we have a 7 bits. So, apply this product 2 into 2 into 2 into 2 into and so on 7. Therefore, 2 power 7, which is equal to 128 different bit string of length 7. So, this way we can apply the different bit string of length 7 can do for bringing the what? Bit string of length. Next example, how many different license plates can be made if each plate contains a sequence of 3 upper English letter followed by 3 letters, and no sequence of letters are prohibited even if they are obscene. Now, we are having 26 choices for each of the 3 uppercase English letter and 10 choices for each of the 3 digits. By the product rule, there are what? 3 times of 26 and then 3 times of 10. Therefore, 26 power 3 into 10 power 3. So, which is equal to 17,576,000 possible license plates. So, this way we can use different license plates can be made. Next example is a counting function. How many functions are there for a set with m elements to set with n elements? Usually, the function corresponding to one of the n elements in the codomain for each of the m element in the domain. See, this is a map from domain to codomain. This is domain, this is codomain. Now, every element in domain must have a unique image in codomain. So, this is the meaning of function. Now, keep it in mind of the definition of the function. So, here a function corresponding to choice of one of the n elements in the codomain for each of the m element in domain. Now, the product rule, there are n into n into n into and so on, m times you have to use. Therefore, we have n power m functions from a set with m elements to one with n elements. Therefore, for example, we have a 5 elements in the codomain. For each of the 3 elements in the domain, we have 5 cube equal to 125 different functions from a set with 3 elements to the set with 5 elements. So, this way we can understand the counting function using this product rule. Next example, counting one-to-one function. See, already we discussed the meaning of functions. Function mean domain to codomain, you have to take it. A map exists from domain to codomain. Distinct element in domain must have distinct images in codomain, or same images in domain. So, this is the meaning of one-to-one function. So, keep it in mind this. Let us go to discuss with counting one-to-one functions. How many one-to-one functions are there from a set with m elements to 1 with n elements? One-to-one functions are there from a set with m elements to 1 with n elements. First, note that when m is greater than n, so there are no one-to-one function from a set with m elements to set with n elements, because m is greater than n. Now, let m is less than or equal to n. What you have to do? Suppose the elements in the domain are m elements, say a1, a2, a3 and so on am. There are n ways to choose the values of the function at a1. It's the first way, because the function is one-to-one. The value of the function a2 can be picked with n minus 1 ways, because the values used for a1 cannot be used again. In general, the value of the domain at ak can be chosen in n minus k plus 1 ways. Therefore, according to the product rule, it has n into n minus 1 into n minus 2 into n minus m plus 1 ways of one-to-one function from a set with m elements to the 1 with n elements. So, this is the mathematical induction way to do that, 1, 2, 3 and so on m. Now, with the help of the product rule, each having n, n minus 1, n minus 2 and so on, n minus m plus 1, one-to-one function from a set with m elements to the 1 with n elements. Now, we have an example. Suppose there are the elements 5, 4, 3 like that. Now, simply the product them, it becomes 60. Therefore, 60 one-to-one function from a set with 3 elements to set with 5 elements. So, this is an example of what one-to-one function are there from a set with m element to one with n element. Next example, what is the value of k after the following code where n1, n2 and so on nm are positive integer has been executed. That is, when k is equal to 0 for I1 equal to 1 to n1, for I2 equal to 1 to n2 and so on, for Im equal to 1 to nm, where k is equal to k plus 1 like that. So, this is the question how we can execute this for the value of k. Now, you have to take from the first step. Initially we have k is 0, 1 is added to k. So, let Ti be the task of traversing the ith loop. The number of times the loop is traversed is the number of ways to do the task T1, T2, T3 and so on Tm. The number of ways to carry out the task Tj, where j equal to 1, 2, 3 and so on m is nj, once for each integer ij, with 1 less than or equal to ij less than or equal to nj. Now, according to the product rule, it follows that n1 to nm times, therefore, the final value of k is n1 into n2 into so on nm. So, this way we can execute the value of the k. Now, another example, counting subset of a finite set. You know what is a set? Set is a collection of well defined object, right, collection of well defined object, and a subset is a, say for example, it has a 5 element, it has 3 elements, then it is said to be subset. Say for example, it consists of 1, 2, 3, 4, 5, then it becomes 1, 2, 3 like that. This is also subset, 4, 5 also subset. What are all the elements in the superset? That should be in the subset. Number of elements in that set is finite, then it is said to be finite set. Now, we are having a general idea, set of all natural number, set of all whole number, set of all integer, set of all rational, set of all irrational, and then real complex. So, superset is complex. So, this way we can have a what, a set, a number system. So, keep in mind, so we understood that what is a natural number, whole number, integer, rational, irrational, real, complex. Now, these are all the set. Number of element in that set is finite, then it is said to be finite set. You take any set which is lesser than that whole superset is said to be subset, and then the same element of that number may be or less than that number is also a subset. Now, we have a statement counting subsets of a finite set. Now, use the product rule to show the number of different subset of the finite set S is 2 power S. There is 2 power cardinality of that set, right. Now, we have a power set. You know what is the meaning of power set. So, let S be one set like that 1, 2, 3. Now, what are all the subset of S is empty set 1, 2, 3, 1, 2, 2, 3, 1, 3, 1, 2, 3. So, these are all the possible subset of S. Now, what is the power set of S, right? So, the P of S is equal to totally it comes of 8, 1, 2, 3, 4, 5, 6, 7, 8. So, 2 power 3 equal to 8. So, this is the meaning of, if this is a finite set, this is a subset, then the coordinate of this power set is P of s equal to 2 power 3 equal to 8. This we know very well. Keep it in mind this. The solution is, let S be a finite set, list the elements of S in arbitrary order. Recall from the previous problem section that there is a one-to-one correspondence between the subset S and bit string of length. Namely, a subset of S is associated with bit string with a 1 in the ith position. The ith element in the list is in the subset and zeros in this position otherwise. Therefore, by the product rule, there are 2 power cardinality of S, modulus of S, bit string of length cardinality of S. Say S equal to 1, 2, 3, then 2 power, right, cardinality of 3 equal to 2 power 3 equal to 8. So, 8 possible subset. This is also comes under the counting principle, under the topic of counting subsets of a finite set. Next, we have one more example. What is the value of k after the following code, where n1, n2 and so on nm are positive integers has been executed? Now, let us start with k equal to 0 for I1 equal to 1 to n1 and k colon equal to k plus 1, for I2 equal to 1 to n2, for k equal to k plus 1 and so on, for Im equal to 1 to nm and k equal to k plus 1. So, this is the program they given, and value of k how to execute. The solution is, initial value of k is 0. So, this block of code made of m different loops. Each time a loop is transferred, one is added to k to determine the value of k after this code has been executed. We need to determine how many times we traverse the loop. Note that there are ni ways to traverse the ith loop, because we only traverse one loop at a time. The sum rule shows that the final value of k, which is the number of ways to transfer one of the m loops, is n1 plus n2 plus n3 and so on nm. So, this way we can find the value of k using the counting principle under product rule. Now, let us going to discuss the sum rule, and before going to solve the problem, all of us we should know what is the meaning of sum rule. If a task can be done either in one of n1 ways or in one of n2 ways, where none of the set n1 ways is same as any of the set n2 ways, then there are n1 plus n2 ways to do the task. So, this is the meaning of sum rule. So, we are going to explain some example related to sum rule. Suppose that either a member of mathematics faculty or student who is mathematics major is chosen as a representative to a university committee. How many different choices are there for this representative? If there are 37 members of the mathematics faculty and 83 mathematics majors, and no one is both the faculty members and a student. So, this is a question. Now, let us start the solution. Here it consists of 31 ways of members of the mathematician faculty and 83 ways to choose the student who is mathematics major. Now, choosing a member of the mathematics faculty is never same as the choosing the student who is mathematics major, because no one is both a faculty member and a student. Now, if statement comes like that, n1 ways is the same as any set of n2 ways, but none of them in the same, that is one of n1 ways or in one of n2 ways. If it comes like that, then we can apply what? Sum rule, like it follows that simply add the ways of 37 and 83 ways of choosing the student of mathematics major. Therefore, 37 plus 83 equal to 120 possible ways to pick this representative. So, this is the meaning of sum rule. Now, we are going to discuss another example. A student can choose a computer project from one of the three lists. The three lists can contain 23, 15 and 19 possible projects respectively. No project is on more than one list. How many possible projects are there to choose from? So, here we are having a three list in the computer project, and then you call it as first one is first list, second list and third list, second is second list, third is third list, and then we have to choose the project, and among these we have to select the project either from first or second or third, but no project is on more than one list. Like that you have to follow the rule. If it obey like that, simply we have to add these three list numbers like 23 and 15 and 19, so that the sum of them is 57 ways to choose a project. So, this is called it as sum rule. Another example, what is the value of k after the following code? n1, n2 and so on, nm or positive integer has been executed. So, the loop formation is k equal to 0 for i1 equal to 1 to n1, k equal to k plus 1 for i2 equal to 1 to n2, k equal to k plus 1 and so on for im equal to 1 to nm and k equal to k plus 1. Now, the solution is, initially we chosen k is 0. The block code is made up of m different loops. Each time loop is traversed, one is added to k. To determine the value of k after this code has been executed, we need to determine how many times we traverse a loop. Note that there are ni ways to traverse the ith loop, because we only traverse one loop at a time. Therefore, the sum rule shows that the final value of k, which is the number of ways to traverse one of the m loops, is sum them like n1 plus n2 and so on plus nm. So, this is the way we can find the value of k after following this code. So, this way it can be executed. Next example, each user on a computer system has a password, every one of you know, which is 6 to 8 characters long, where each character is an uppercase letter or a digit. Each password must contain at least one digit. How many possible passwords are there? This is the question. Now, the solution is, let P be the total number of possible passwords. So, let it be 6 to 8, therefore, P6, P7, P8. Now, these denote the number of possible passwords of length 6, 7 and 8 respectively. Now, according to some rule, this becomes what? P6 plus P7 plus P8. Now, we will now find P6, P7 and P8. For finding P6 directly is difficult. For finding P6, it is easier to find the number of strings of uppercase letter and digit that are 6 characters long, including those with no digits, and subtract from this number of the string with no digit. By the product rule, the number of strings of the 6 character is 36 power 6. Therefore, the number of strings with no digit is 26 power 6. Hence, the rule is P6 equal to 36 power 6 minus 26 power 6, which is equal to 2176782 336 minus 308 915 776. Subtract them, the value of 26 power 6 and 36 power 6, so that we have 18678666560 value. Similarly, we have P7 is 36 power 7 and 26 power 7, and subtract them, and corresponding value is 70332353920, and P8 equal to 36 power 8 minus 26 power 8, which is equal to 2612 282 2842 880. Consequently, the 3 value, add them, that is sum rule, right. So, we have P equal to P6 plus P7 plus P8 equal to this value. So, this way we can use the password of the computer system. So, these are all the possibilities of the password. Using counting principle can determine the password. Next, subtraction rule. Subtraction rules states that if a task can be done in either n1 ways or n2 ways, then the number of ways to do the task is n1 plus n2 minus the number of ways to do the tasks that are common to the different ways. So, this is the meaning of subtraction rule. So, the subtraction rule is also known as principle of inclusion and exclusion. That is, if A1 and A2 are two things or two ways, then the union of A1 and A2 is equal to A1 plus A2 minus A1 intersection A2. So, this is called as principle of inclusion and exclusion. Next example, how many bit string of length 8 either start with 1 bit or end with 2 bits 0 0. Now, we have a solution. We can construct a bit string of length 8 that either start with 1 bit or ends with 2 bits. By constructing bit string of length 8 beginning with 1 bit or by constructing a bit string of length 8 that ends with 2 bits 0 0. Now, we can construct a bit string of length 8 that begins with a 1 in 2 power 7 equal to 128 ways, right, because it consists of length 8 and then the bit string of length 8 that begins with 1, therefore 1 reduced totally 2 is 7, therefore 2 power 7, because 2 bits 0 and 1, therefore 2, and 1 is already taken, therefore 8 minus 1 is 7, 2 power 7 equal to 128 ways. So, this follows the product rule, because the first bit can be chosen in only one way and each of the other 7 bit can be chosen in 2 ways. Similarly, we can construct a bit string of length 8 with the 2 bits 0 0 in 2 power 6 equal to 64 ways. This follows by the product rule, because each of the first 6 bits can be chosen in 2 ways and the last 2 bits can be chosen in only one way. Therefore, 2 power 7 of 1 is equal to 128 ways, and 2 power 6 equal to 64 ways, and then 2 power 5 equal to 32 ways. Like that, we have to construct a string. Now, the first bit can be chosen only one way, second bits can be chosen in 6 bits can be chosen in 2 ways, and the last 2 bits can be chosen in one way. Therefore, consequently, the number of bit strings of length 8 that begin with a 1 or end with a 0 0, which equals the number of ways to construct a bit string of length 8 that begins with a 1 or that ends with 0 0. Therefore, this is equal to 128 plus 64 minus 32 equal to 160, that is A union B, right, cardinality of A minus cardinality of B minus cardinality of A intersection B, like that. So, this way we can choose the subtraction rule or principle of inclusion and exclusion. So, A union B equal to mod A mod B plus minus mod A intersection B. Similarly, mod A intersection B is equal to, this way 2 ways we can do for what, principle of inclusion and exclusion. So, either way, this way we can bring it like that. Next example, a computer company receives 350 applications from computer graduates for a job planning a line of new web servers. Suppose that 220 of these applications majored in computer science, 147 majored in business and 51 majored in both computer science and in business. How many of these applicants majored neither in computer science nor in business? So, we have 350 applicants and 220 of these applicants are majored in computer science, 140 majored in business, 51 majored in both computer science and business. Now, to find the number of these applicants who majored neither computer science nor business, that is we required. So, we can subtract the number of students who majored either in computer science or in business or both from the total number of applicants. So, let A1 be the set of students who majored in computer science and A2 be the set of students who majored in business. Therefore, A1 union A2 is the set of students who majored in computer science or business, and A2 and intersection A1 is the set of students who majored both in computer science and business. Now, apply subtraction rule. The number of students who majored either in computer science or in business is, this rule is modulus of A1 union A2 is equal to cardinality of A1 plus cardinality of A2 minus cardinality of A1 intersection A2. Here modulus represent the cardinality, that is cardinality of A1 union A2 is equal to cardinality of A1 plus cardinality of A2 minus cardinality of A1 intersection A2, which is equal to 220 plus 147 minus 51 is equal to 316. Therefore, we can conclude that totally 350 applications, out of 350 applications, and then either computer or business of the number of students is 316, then subtract them, the resultant is 34. 34 applicants are majored in neither in computer science nor in business. So, that is what we have the question, that is the answer to the question. So, 34 applicants are majored in neither in computer science nor in business.